determine where the two parametric curves intersect. So we've got t cubed minus t squared, and our other one, I think this will be a line, 7s minus 1, 3s minus 1. Okay. So, I mean, I could sketch them to get a sense of what's going on, but ultimately we need to put their x-coordinates and their y-coordinates equal to each other and see if we can solve for pairs of s and t that satisfy these equations, both of them at the same time. So what can we do? Well, the second one, we could rearrange it, add 1 to both sides, and isolate for s. That way we can take this s and plug it into the first one, and then we will get an equation just in t. So we'll get t cubed is 7 minus 7t squared over 3 minus 1, but 1 is 3 over 3. So we can get t cubed is 4 minus 7t squared over 3. And we can get a polynomial out of this, multiply by 3 on both sides. And bring everything over to the one side. So if we want values of t that have values of s that satisfy both of these equations, they will be values of t that are roots of this particular cubic. Okay, now the challenge is, well, how can we deal with this? And maybe, just maybe, we have the cubic formula memorized, but I don't. So what can I do? Well, I notice I've got 3, I've got 7, I've got 4, and I know that 3 plus 4 is 7. So is there a way to fiddle with the signs here? Yes, there is. So if I put t is -1, I'll get -3 plus 7 minus 4 is 0. So -1 is a root. I can factor out t plus 1. Okay, just a little bit of playing around here. So we can factor that. We'll get 3t squared. You'll get a minus 4 here. And then what has to go in the middle? Something t. So if we multiply it out, we get t times -4 will give me -4t, but I see no t's in the original expression. So it'll have to be plus 4t. Okay, and then we can use something like the quadratic formula if we wanted to, or we could try and find another root with guess and check. Nothing is immediately springing to mind, although I've got 4's here. I wonder if I make t 2. 3 times 2 squared, that'll be 12 plus 8 minus 4. No, that's way too much. -2? Let's see. -2, so you'll get 12 minus 8 minus 4. Okay, that'll work. But of course, we could use the quadratic formula if we didn't want to stop to factor. It's always a bit of a gamble. Should I stop and factor? Because if you can't think of anything, or you miss the obvious, then you've wasted your own time. Whereas the quadratic formula might be a little unpleasant, but it always works. It's guaranteed every time. So this means our values of t could be -1, -2, or 2/3. Now, not necessarily all of them will lead to values for s, okay? But we do have this nice expression. S is 1 minus t squared over 3. And so for t is -1, we get s is 1 minus -1 squared is 1 over 3. S is going to be 0. For t -2, we get s is 1 minus 4 over 3, so s would be -1. And for 2/3, it was 2/3, right? Yeah, 2/3. We will have s is 1 minus 4/9 over 3. So that'll be 5/9 over 3, 5/27. Okay, so we do get a t and a corresponding s. The only thing to do is to absolutely make sure that somehow the algebra hasn't screwed up. This doesn't happen so much for two-dimensional stuff, but if you move on to 3- and 4-dimensional parametric curves, which we're not doing in this question, but you definitely want to get in the habit of checking everything. So we'll do t is -1, s is 0. T is -2, s is -1. Oops. And our last situation, t is 2/3, s is 9/27. Okay. So, so it's t cubed negative t squared. So that'll be -1, negative of -1 will be -1. We'll get -8 and negative of 4. And then 8/27 and then negative of 4/9. All right. The s expression, what was that curve? 7s - 1, 3s - 1. Okay, so plugging in 0 is pretty easy. -1, -1. Okay, great. -1, -1 is a point of intersection. Let's see. -7 - 1 will give us a -8. And then -3 times 1 will be -3. -1 is -4. So we get another agreement, another point of intersection. And I bet the last one works too. 7 times 9, 63/27. Let's do a little side calculation. 63/27 - 1. Okay, 63 - 27. Okay. 13 - 7, 6. So 36/27. Okay. And we get... Somehow that seems a little... Oh, no. So it doesn't... It looks like we're wrong here. Okay. 7 times 9, so that'd be 63/27, minus 1, so that'd be minus 27/27. So 36/27 is not 8/27. Okay. So just quickly, because I was expecting that one to work out fine. Oh, s is 5/27, that's why. I should have caught that. 9/27, why wouldn't I just write 1/3? Okay, so going back and trying that again, that'll be 35/27. The reason I was expecting it is the other ones worked, and I'm pretty sure this is a line, and this is sort of a cubic, so I'd expect 3 intersections. 35 - 27 is 8, so 8/27, that works. And then, as I said, the last one should work. 15/27 minus 1. So that'll be 15 - 27, -12. -12/27, divide both by 3, and you get -4/9. That one works as well. So the points of intersection are -1, -1, -8, -4. And the last one that we had a little bit of trouble with, 8/27. -4/9. And there they all are. All 3 of them. And I do believe, if you sketch it, you get something that looks a little like this. And the line, I guess, because it's got to get hit a couple times, it's going to look something like this. Okay. But we didn't sketch to make a guess as to how many there were. We really did just follow the S's and T's as we solved for them, and that's how you handle the points of intersection.